We have what we called a brain hub. Hippocampus, for example, a well-known nervous center, is involved also in emotional states, also in reasoning.
Hello, everyone. Welcome to the Data Innovation Podcast. Language is something that we actually use every day without effort. But to understand the way how it works is not that simple. With the rise of large language models, we are faced with new questions or interesting questions like, how are humans or machines processing language? Are they doing it in a similar way or fundamentally different? To explore this question, we are joined today by Claudiu Barbu. Claudiu, welcome. Tell us who you are.
Hello, Anna. Hello to our listeners. Thank you for inviting me. I'm Claudiu Barbu. I work at E.ON Digital Technology as an AI engineer. I had a little bit of experience in academia. I teach statistics during my first PhD. I have 2 books published, but I think the most relevant part of my studies for this podcast is my first BA, which is in psychology. That time I was researching and I was studying for 4 years how humans, how us are understanding the language. And my BA thesis is what's related to what's the role of working memory and inhibition in human language disambiguation. So thank you again for having me. Hope to share some knowledge. Hope to have some impact.
The pleasure is ours. Thank you so much for joining us. And yes, like you, I am exactly the same, excited about knowing the answers about different questions related to these similarities about how these processes are working, machine and human. And Claudio, you are one expert in this area. I appreciate very much that you are here, helping us to understand how these mechanisms are working. Maybe some of our audience or most of our audience already have heard about tokenization or token prediction by LLM. But tell us, how is it the case by humans? How are humans, we are processing sentences? Can be these also considered like a prediction task or prediction mechanism? I am very curious, or it is completely different?
So let's start with the similarities. It's well documented that we understand language as structure. So order matters of the words, of the tokens. We call it lemmas, but still tokens. So on this aspect, we have similarity between how LLM are processing the language and how us are processing the language. Also, when we think about our concepts, we do not store the concepts as in dictionary. You have entries, you have definition. We represent concepts in a similar way as embeddings. We have a sort of neural activation for each concept. We have also an algorithm that explains how we are understanding text every moment we are reading it. Every item, every token, every word that we are reading it, we integrated into the closest semi-structure that we build. This is the minimal attachment heuristic. Also, every item that we are reading, we are integrated into a structure that it's not complete, that it's building. This is called late closure. More than that, even without knowing the grammar, we keep in mind the meaning, the representation of a noun until we meet a verb. We keep in mind the representation of an adjective until we meet a noun. So if you think about the comparison between us as a cognitive system with LLMs, of course, maybe LLM do not do the same stuff because you have a sequence of tokens, you use the positional encoder, then you feed everything to the attention mechanism, those query keys and value matrices, and you multiply it and you get the attention. It's not the similar thing. But if you think about algorithms and what I said, the representation based on activation of concepts, we might think about something that is similar to computational. However, if we think also about the characteristic of human processing, the similarities stops here, because I mentioned we are representing concepts as embeddings, okay, as a representation. Representations are not just the way we use embeddings, which have the same values for every token in the vector of embeddings. We have the same value, we have the same order if we use the same model for embeddings. Here it's not the same. If we listen, for example, to a story for the first time, some part of the brain gets activated. If we listen for a second time, another part of the brain will get activated. More, if we don't know about that story and someone tell us this story, it will be about this topic, where we get a picture about it, and then we listen to the story, another part of the brain will be activated, and the differences continues. For example, if we try to map the embeddings to some part of the brain, like I mentioned, also it doesn't work, because we don't have functionalities related to localization. We have what we called a brain hub. Hippocampus, for example, a well-known nervous center, is involved also in emotional states, also in reasoning. So the same nervous structure is involved into two different topics, cognitive and emotional. We should not think about the brain as a flat structure. The same structure is also involved into cognitive, for example, activities, into emotional activities, and the other way around. The same behavior sometimes activates one part of the brain and sometimes a different part of the brain. Also, there are differences between humans, like individuals. You, for example, if you read the same text as I read it, and if you scan the brain activation on your side, you will have some nervous central activated, I will have different ones. And the comparison also with a model that we're having, because LLM are using the transformer model, also stops here. The brain, it's not just a deep learning model with weights defined by our experience and by our genes, and waiting for stimuli, for situations to react. The brain is active. The brain has what we call the default neural activation. It needs to compute sort of sensors, internal sensors, so it will deal with homeostasis. Homeostasis is assuring the equilibrium of internal body. And more than that, there are studies now that moved this concept of homeostasis way upper, like they call it allostasis, predicting what will happen, predicting a disequilibrium, sort of predictive maintenance, but we call it predictive regulations. So this is, for example, how emotions are built. Lisa Feldman Barrett has a book that was published, I think, 10 years ago, Secret Life of the Brain. So brain has a secret life, and how emotions are made. And even cognitive psychology, which is the most computational part of psychology, said until some years ago, 10 years ago, that emotions are reactions, not to the situation, but to how we interpret it. They're not. The recent study says that emotions are created by brain when he's trying to predict future disequilibrium in homeostasis, which is called allostasis. yeah, different.
Amazing. I really enjoy listening to your answers, and even when I am listening to it, I think how my behavior itself react to some stimulations that, as you said, when I am reading one book is different when you are reading it. And this is, yes, every individual, every personal experience is taking place, is playing a role there. And this is what differentiates us to the mechanism for prediction. Really, really interesting. And tell me another thing where I think it would be good to know as well the differentiation, how these two mechanisms work. When we talk about ambiguity, this is something what I think for us in our brain, it is it is a very, very okay. It is something what for us is difficult to handle. No, sometimes you are understanding this even when you are talking about the same thing is being understood in two different ways. How are large language models treating these ambiguities? Is similar probabilities as well, or is another way to describe this?
LLMs are dealing with ambiguity the same way. I mean, at the moment when they are understanding the text, they are dealing with ambiguity the same way they are dealing with every other word, they are dealing with every other tokens. For them, it's just you have a set of tokens in an ordered manner. You have, like I mentioned before, the positional encoder, you feed it to the attention mechanism. This is how they understand what's there. Us as humans, when we meet an ambiguous word, we keep at least two activations in mind. We know that word is ambiguous, and we keep, if the ambiguous word has two meanings, we keep the two meanings activated in our working memory. What is important, because I studied this for a long time, is individual differences, and also how frequent is one meaning compared to another. If we think about this ambiguization, if the ambiguous word has a frequent meaning in English or in the language that we speak, and later we found out that the disambiguization was towards that frequent meaning, we don't have usually a problem. But if the disambiguization is related to the less frequent meaning, the individuals, the person that don't have such a high developed working memory will have problem with this, especially if the disambiguization came after a certain word. For example, if I have the ambiguous word now, and after two words I get the disambiguization, it might be okay, no matter the meaning of it. If it's the most frequent one or if it's less frequent one. But if I put 10 words between the ambiguous word and the disambiguization, and the disambiguization is towards the less frequent meaning, the persons with not such high working memory capacity will have problems with understanding the meaning of the ambiguous word. Also, another function that is involved in this process is attention, but I'm not meaning attention like in Transformers architecture, attention mechanism for us, for humans. And what I mean by attention mechanism is one specific function, inhibiting the less relevant information. In this case, we should inhibit the meaning of the ambiguous word that we already know it doesn't apply in this sentence. If we can do that, we might understand faster the meaning of the ambiguous word, no matter which frequent or less frequent it happens. But if we cannot do this very fast, And it's also, if the disambiguation comes towards the less frequent meaning, we have problem inhibiting the more frequent word, because by default, that more frequent meaning of the disambiguation is activated in our working memory, because we used it every day in the current language. So that's the difference.
It's after this explanation, it's somehow clear, no? That it works with frequency as well.
Yeah,
no? That
yeah.
means we are talking here about statistics or probabilities as well in that case.
Yeah, for words, for lemmas in the current language, exactly.
Amazing, great. That means this explains as well a lot the increasing usage of semantic in the large language models. That means this is fundamental to use semantic in those models. Explain us why.
Yes, I mean, the LLMs are capturing the semantics at the beginning with embeddings, and then when they have to predict the next token in order to create a sort of coherence of based on the input, the prompt, whatever we have in the system prompt, whatever we add in the system prompt, it's all a prompt, and then expect a generative action from the LLM. They are doing it not by predicting the next token, but by predicting the next sequence of tokens. We heard a lot of times, yeah, LLM predicts just the next token, predicts the sequence of tokens is different. Why? When you have all of the words in the vocabulary, after all of the attention mechanism has processed the tokens, you got some attentions, then you got some logits. If you put softmax activation on the logits, you get probability. But what you can do is not just taking the token with the highest probability. You do multinomial search, multinomial sample search, and you take 4 or 5 tokens from the ones that have high probability. Because this is important, softmax activation also favors the logit that had the higher value before applying the softmax activation. So we don't want to use just one token, the one with the higher probability. Softmax already increased that compared to the others. We take the tokens with the highest probability, sampling from the one that have high probability, and then we continue at the next iteration. We do not just compute the probability of the next token. We compute already a sequence of 2. The probability of the tokens we choose first time with the probability of the tokens we choose at the second iteration, and there are also 4. And there's a combination from the first 4 to the first 4. And now we're not computing just one probability. We're computing a multiplication of probabilities. And this is towards, at the end, we get a long-term coherence. And we can use, with this sampling, we can use beam search. We can use contrastive search if we want to use, if we want to get more differentiations in the output of the LLM. We're not doing this. I mean, we as humans know what we want to answer, even if we can have a computational model, because McClelland and Rumelhart already did that like in the 80s, which was, I don't know, like 20 years before the attention is all you need, the paper from Google that show us how transformer model works. So even if we compute that, we have a reason, we have a meaning already after we read something. We do not just treat the text that we read or we hear as just a sequence of token and okay, based on what are we answering, and then we have multiplication of probabilities. We understand the language. We have this concept of meaning, that it's not just at embeddings. LLMs are dealing with meanings, with semantics at the embeddings level, then there's just computation, there's just prediction with attention, okay, multiplying matrices, then like I mentioned, logits, software activation probabilities. It's just computation. For us, it's not like that.
Computation or mathematics?
Yeah.
Or statistics?
yeah. If you think about, I teach for years.
Combination of all of them.
Yeah, with SPSS, by the way, I teach with SPSS, with R, then with Python.
Yes, it is really, really fascinating to hear these explanations and to understand or to try to understand how our brain works. In the case of the machine is, let's say, more explainable, if we want to say, because I think we are, as individuals, as human beings, so complex. And as you explained, there are so many factors, emotions, situations, contextual situations, and so on. Just a closing question. What do you think, or do you think that machines are going to reach the level of humans by reasoning or by language?
In this case, I would say they are missing some parts, like we discussed, understanding the text at a higher level than embeddings. They also are dependent right now of humans when they are generating the task, when they are computing it. Also, error correction. Sometimes it works, sometimes it doesn't. I would say I see a sort of tendency towards redefining some concepts that in the latest years were supposed to be cognitive concepts, and now I see a sort of definition in weakening those terms. I am seeing lately a tendency to redefine certain concepts that used to be psychological per se or cognitive per se. And here I mean general intelligence. General intelligence has always been defined like having performance in a huge variety of tasks based on generalization. Based on generalization, this is important. Now I see a tendency towards redefining this in terms of benchmarking success, which is not the same thing. The same output, the same answer, the same response can be acquired by two different processes. If an LLM performs best at some benchmark, it doesn't mean it has similar reasoning as human, right? It has the same output. So we need to think more deep towards what's behind an answer,
without only considering only the output.
The output.
Yeah,
because
this is a good yes.
If we only look at the output, we might just have a plausible theory, plausibility. We can consider that because an LLM had some success on a benchmark task, it had involved the same reasoning mechanism that the human does. But this is just a plausibility, it's just an assumption. As you know from testing hypothesis, a theory not just needs to be plausible, we need to falsify it, we need to test him with the probability of the second type of error, with the null hypothesis and so on. Only that, if we cannot do that, it doesn't mean we have evidence-based. It means we just have a plausible theory.
Yeah. Yes. That means this is something what we can follow the development of these topics, and I think it deserves to be followed as well, how they are evolving. And yes, I hope for most of you it was one inspiration and it brought a lot of insights, a lot of knowledge. For me, it was amazing, this journey with you, Claudiu. I am very, very thankful for joining us.
Yeah, I'm also thankful for inviting me, and I hope the listener have now a better understanding of how humans understand language.
Yes, and you can communicate it to us. Did you learn from this podcast? We hope. Do you have any question to Claudiu? Then let us know your questions, and thank you for joining us. And I see you the next time. Bye bye.